just like conveniently assume like one thing and give the important definitions kind of faster. And it's like a more intuitive presentation, and I think that's just gonna like help people just kind of swallow the kind of difference between like the approach that I'm taking here and the like traditional consensus protocol kind of approach.
Nice.
I would love to go into it, but maybe that was my quick update from to do the wide then deep kind of protocol.
Cool. That's I'd love to hear more about it. Actually, I can do
Greg?
A lot of fun stuff. But with respect to getting all of the definitions for the consensus as trace, last week I spent a little bit of time on the middle component of the triple that constitutes the type. And the one thing I mentioned but didn't go into was the subtyping part. So I secured all that, wrote that all down, and it also requires the notion of a polarized version of the core calculus. So, and that is consistent with the need to have it be polarized in the double perp closed components. So,
does polarized mean that like all the nodes agree in the end?
No.
Polarized mean?
Polarized just means that if you have a channel, then you use the channel
in one direction, not the other.
Yeah, only in one direction. So that's what creates the need for twisted pairs, right? So if a contract P wants to communicate with contract Q, then P has two channels to Q. One is a write channel, at a minimum, has two channels to Q. One has a write channel and a read channel, and Q has the other ends of those channels. So that's it was pleasant that both the middle component and the two double perp closed components, they both require this twisted pair construction, or this polarized construction, and they line up perfectly. So that's nice. And then having the subtyping relationship all well spec'd is also very nice. So that's what I worked on over the last week.
Cool.
Yeah, I can go into details, but I put respecting wide versus deep. I'll hand the baton over.
Sounds good. Carl, how are you?
Cool. Yeah. So wide versus deep. This will be very short. I have reached yet another milestone in the adding Casper to Pytherium. It is to the point where I would say like 80%. It's all there. It just needs to be a little cleaner and nicer. So.
Do you mean that it's running?
Yeah, it's running. Like, so you can, so you have like fork choice, you have the whole stuff that Vitalik has written, the Casper contract, so like slashing, etc. What you don't have is validator logic. That is something I need to add in. Like,
I see.
A simple bot to tell, to vote on.
But does the fork choice involve the looking at the checkpoints and stuff like that?
Yeah, exactly. Cool. So like, great. How much weight does this have versus the head, etc.
Neat. That's pretty cool.
Yeah, super exciting.
Anyone else?
Who else is here?
I don't know. There's a couple of people, but
Okay.
we can just.
Yeah. Okay. Cool.
So should we start going a little deeper?
Yeah. Sounds good.
Yeah, I can talk about this. This kind of like these definitions that I'm working on. Basically, the important one. So first, like the way I'm kind of setting up the presentation is there's like, you can kind of try to define consensus protocols for to like produce consensus safety and consensus liveness, or you can design them to produce estimate safety and estimate liveness. And there's like this relationship, which is that if you decide on an estimate once it's safe, like once it has estimate safety, then like that's a consensus protocol that has consensus safety. And the idea is that safety for consensus protocols means that if two nodes decide the same value. Liveness means that they eventually decide on a value. In estimate safety is that a node's value won't change. And then liveness means that it'll get to a point where it won't change, if it isn't already there. So they're kind of, they're different definitions, but there's like this relationship that kind of ties them together really nicely, which is to say that like all consensus protocols that have decision rules that only decide on estimates after they get estimate safety have consensus safety. So you can like add a decision to a protocol with estimate safety, and then it gets consensus safety. But like, making that decision isn't necessarily the whole point of the protocol. Like the protocol is just trying to maximize estimate safety as opposed to produce consensus decisions. So basically what I'm doing is I'm kind of, I give a little like proof of that. And I only really rely on, like this assumption, which I realized kind of implies the tie-breaking property. So I don't need to like assume the tie-breaking property. I can just kind of assume this instead. The assumption basically is that like two protocol following nodes who have received the same set of message have the same estimates. And that assumption turns out to be like super useful in proving things, and like also because it gives us tie breaking. I don't really have a name for that property at the moment. Maybe you guys do. If like again, protocol is such that if two nodes see the same set of messages, they make the same estimates.
It's determinism.
But
same
it's also
same inputs, same outputs.
Kind of, yeah. But it's also not affected by the order of the messages.
Yeah,
so it's like a set of messages. Yeah.
As long as it's set, then it's determinism, because the input is the set.
Determinism, but you can have a deterministic thing that keeps track of the order. I guess it's like a deterministic set function.
That's right.
On the view.
That's right.
Yeah. So basically I just like assume that my estimate safety protocol, or like the consensus protocol that I'm talking about, has this property that nodes make estimates based on this deterministic function of a set of their inputs, or like that it can be understood that way, right? That you have this basic invariance. So with that, I can prove the tie-breaking property. Basically, because if A and B send each other their views, then they will in the end each have the union of their views, and then they'll have the same estimate. which means that like one of them was able to convince the other if they had a different estimate initially. And that's kind of like all the tie breaking that we really need.
Cool.
For at least for at least that I've needed so far. So and then the part that I'm kind of on right now is trying to talk about and like make really clear this idea of like why, if there's F Byzantine faults and they might be offline or they might equivocate, it doesn't mean that they can be both equivocate and be offline. There's like this, like, if there's like 33 Byzantine nodes, like they can't both be offline to prevent the quorum and equivocate as part of what you're doing. And so I kind of like, I'm trying to find a super crystal clear way to advocate for why we should be trying to like get as much Byzantine fault tolerance as possible, rather than to just kind of like decide at the outset what our decision threshold is and then like be stuck with 33% as a result. And basically the case is that if we happen to get more safety, then like there's no question about whether the nodes will be available into the future. So once you have the safety, the liveness question is kind of like, moot. Before you have the safety, the liveness question is kind of very important. But like normally the reason why we have like this 1/3 bound in like traditional consensus protocols is that we have like a certain size that you need in order to tolerate a given number of faults, and that size is like growing in the number of faults, and then you have the number of nodes that are available falling in the number of faults, and like you need the nodes to be available to have liveness, and you need to like tolerate equivocation to have safety. So there's like this classic like 33% bound, and I'm kind of trying to like make this case that like by postponing decisions, by moving decisions kind of out of the protocol, and only doing estimate safety, we don't have to kind of speculate about how Byzantine nodes are just as likely to be Byzantine nodes are equally likely to 100% be equivocating or 100% be offline, which is kind of like the normal model. If you're thinking about trying to get both safety and liveness for consensus protocol. I don't know. Did that make any sense for anyone?
Yeah, that made sense.
Yeah.
Yeah, and I like the idea of moving decisions out of the protocol, because also, it kind of gets rid of these situations where a coalition with the fault tolerance with n minus the fault tolerance nodes has like infinite power, or like just as much power as a coalition with one additional node. Whereas like if you're just producing as much safety as possible, every additional node contributes, as opposed to having just like this fixed quorum size for a decision in a consensus protocol.
That's a nice property.
Yeah, and the main challenges in that, in doing the out of band, I'm curious, what are the main challenges? Sorry, what are the main challenges in doing it out of band?
I mean, basically, like, it's not that challenging. I mean, you just pick a safety threshold, and then when your estimate safety gets up to that threshold, decide. There's like a relatively super trivial rule for deciding. You just have to pick the threshold, right? And I'm just saying, maybe that threshold shouldn't be in the protocol.
Yeah.
Wait, so you're saying the threshold should be a part? Threshold decision making should be a part of the protocol?
No. So but it's not consensus, right? Like it's not that everyone has or everyone knows each other's decision thresholds.
Okay, that's what I was asking. Yeah.
So like it's part of the client protocol.
Wait. How do you keep your determinism property if everyone has a distinct threshold?
The determinism property is only for the estimate kind of thing. It's not really for decisions. As soon as you go into decisions, you basically just treat them as like separate objects. Right, and then you say, oh, look, I've had this decision. Even though if I were to calculate my estimate, I would get a different value. I'm just not ever going to do that again. But yeah, I mean, once you have decisions, you kind of have it kind of breaks this determinism in some way. But you can imagine basically that it's like a separate protocol, right? One protocol for making decisions and one protocol for getting the estimates, and the estimates just get more and more safe, hopefully. And then like the people who make decisions, may be left behind if.
Yeah. So there's a kind of there's a tension between decisions and this determinism property.
Yeah, that's right. And also the there's like a difference in kind of trying to provide a consensus protocol for consensus safety, which is a property kind of the protocol, or versus estimate safety, which is parametric in the current state of the protocol.
Mm-hmm.
So rather than I think really this is what kind of proof of work does also. Rather than providing like consensus, it provides like estimate safety, which anyone can kind of use for consensus just by making decisions after a certain number of points.
Yeah, it's a module.
Yeah,
it's a library or a piece of a consensus protocol.
Mm-hmm. Yeah, and then one idea there is like, okay, maybe the full node protocol is like to not have decisions, but like most people don't run full nodes so that they can just economize and make decisions. And then what will happen is like when there's consensus failure, there'll be like a relatively large number of faults depending on the people's different, but also depends on people will lose consensus based on whether those faults are like more than the faults that their estimate safety had when they made their initial decision.
Yeah, understood. The decision is the waveform collapse, right? You don't get to be in superposition anymore.
Yeah, it's kind of outputting a value, just the way like traditional.
Yeah, no, it turns the thing into a function. Right? There's an observed value. I mean, that's what's interesting about the consensus is that it's not actually a process, right? It's a function. Where I hear you.
There's a bunch of process.
I make a distinction between functions and processes. In the every function is a process, but a function is a special kind of process that ultimately produces a result, right? So from some observed set of inputs, whether they're passed in through message passing or whatever, then eventually you can get an output. Whereas a process does not have to have that property. An example, one of the classic examples, of course, is the high watermark protocol, which is what's used in TCP/IP. For to maintain the property of exactly once in order delivery, right? So the property is a property of the channel. You know that the channel that's being utilized when you pump messages from one side to the other, both sides see the messages in exactly the same order, and they don't see any duplicates. So that's a property of the channel that's maintained by the high watermark or sliding window protocol. So that's not computing a value, right?
So maybe like consensus protocols compute a value and like estimate protocols don't. It's easy to turn one into something that computes a value by basically just like choosing a point when to output a value.
Mm-hmm.
I just think and basically there's this thing where like if there's enough equivocation, then like an estimate can change. Basically, the only way to like to kind of not have that is to like weaken our assumption about the determinism, and we're basically like, if there's a tie, then you go with the one you picked first, which I think is, probably like, I probably like it just because it lets me say, 100% is the fault tolerance for the estimate. But it is maybe a little misleading, because you lose consensus safety even though you don't lose estimate safety once you get to that amount of faults. And the other thing is, like, I don't want to necessarily let go of my determinism assumption, because like it is super convenient for simplifying a bunch of proofs. Like, although, like, I know that I can weaken it and have have just like different proofs, I guess.
What are the ways it's robust against weak, and what kinds of weakened forms do you consider?
So basically, the reason why estimate safe. So the thing that I really get out of my assumption is like simplification to my proof that you can make estimate safety into like a decision with consensus safety, where basically I'm proving that two nodes with same estimates have two nodes with safe estimates have the same estimates. And the way I kind of do it is by like looking at the estimate in the union of their views. But however, I think that's kind of a shortcut. I think I could do it through like this kind of adversary more reasoning, which is which I've basically excluded at the moment. Well, not excluded. I'm just kind of leaving it as like more like an implementation detail than like the core theory. But I think that like basically the proof that estimate safety will provide consensus safety is going to be a little more complicated if they don't have the same estimate when they see the other party's view. Now, I'm confident that I can still make a proof that like works, except for maybe like the tie breaking, like because of tie breaking issues.
Yeah, I've often felt that the tie breaking property is an extremely strong assumption.
Oh, I mean, so I run into issues if I get rid of it. Yeah.
No, of course, but it's a very powerful property of a system to have.
Yeah, but there's so many ways to achieve it. I've thought of like multiple ways to do it. I mean, I'm not basically like all of them kind of use cryptography to add a random epsilon in a different way.
Cool.
But you're right. It does require like this kind of like cryptographic assumption, therefore, or like a source of entropy that you relied on or something. It isn't trivial, but we're already making cryptographic assumptions. So
yeah, no, I mean, I'm not saying that it's not I don't think it's an unreasonable property to assume. It's just that it's a very strong one. Yeah.
I think there might be I think the version of tie breaking that comes out of the union, like two nodes with the same view having the same estimates, might be a little bit weaker because it doesn't say anything about the weights of the subsets of nodes. It just basically says that kind of like implicitly that if like A communicates all their messages to B and B communicates all their messages to A, and if they disagreed, then like definitely one of them will convince the other.
Yeah, that's a very strong assumption.
But I'm not sure. It might be weaker than tie break, the normal than the form of the tie breaking assumption that I had earlier.
Oh, yeah. Well,
Because I don't have to. Because I don't have any weights. I don't need to define weights.
yeah, but right. I mean, it just doesn't occur in, for example, in humans, right? That's why we have forks.
Oh yeah, no, I hear you, but it's just nice not to deal with this like edge case.
Yeah, I understand.
Edge cases create all sorts of weirdness, also, right? Like in game theory, it can happen.
What I was arguing about a month ago when I got back from Spain was that the real market is choice. So you essentially trade cash for choice. So if you want to be the decider in a tie, then you give up cash, and the other party is likewise is willing to give up choice in order to have cash, which might mean having choices later down the road.
So that doesn't sound too bad, but the thing that I don't like about it immediately is that it's kind of interactive. Whereas like all the crypto ones that I know, like it's just like, oh, there's like some kind of hash race that determines it.
Understood.
Or there's like initially a random weight.
Yeah, I understand. I really liked it because even though it's interactive, it sort of gets at the heart of the trade-off, right? Basically, an agent is willing to give up its option in order to secure future option later.
Right. Mm-hmm. Yeah, that's kind of interesting. Imagine if, for example, people like pooled their transact, so like in my sharding solution, I do have like a separation of like transaction receipt and then transaction processing order. There's like a kind of scheduling that needs to happen.
Yeah.
And this could be a similar thing where basically like you have like an intermediate step where like the scheduling is resulting from some like, market mechanism clearing this market for priority.
Right. And that's what it came down to is remember I had all these qualms about, a market
paying for liveness.
Yeah, paying for liveness. That's right. That made me extremely nervous. But then I thought, well, it's better if there's a market than if you get no choice at all.
Mm-hmm. Yeah. And the other thing is like often if there is a market, if there's going to be a market anyways, if there's enough demand for there to be a market anyways, it makes sense to do everything you can to reduce the cost of that market in terms of the complexity of that market settlement mechanism and stuff like that, right? Basically, like any transaction cost is going to significantly affect the utility of that market.
So I can go a little deeper if you're done. It's up to you.
I think I'm done. I'm just struggling to articulate things in like a way that's like a more high level.
I thought it was pretty high level. I thought it was very. I'm curious to get feedback from other people who watch the video and see if they grasp. I thought it was a very lucid explanation, but I've been living and breathing this stuff for a while. So
cool. I appreciate that. Right, so go ahead.
Well, I just quickly go over how we needed polarization. And this is joint work with Mike Stay. So we needed polarization to make sure we got the subtyping right. So basically, for the combinator, Vlad, I don't think you were here last time or whenever I introduced looking at these types. I'm just using a toy version rather than the full Roe-Lang version because first of all, these combinators are completely equivalent, and that's one of the things we proved in the recent couple of papers. but also because we don't have to deal with nominal phenomena. We have it all kind of, it's all handled via reflection. So there's no new operators in these combinators. And it's interesting. This is the stopped process. This is the process that's just sending a message. This is a process which will duplicate, whatever gets on A, it duplicates out to B and C. This is a process which kills messages that come in on A. So you'll notice that MA is the only one where A is positive. And then all the others, A is negative. So this is receiving on A, duplicating out to B, receiving on A, throwing it on the floor, forwarding from A to B, and then branch right A, B, and branch left A, B. And then I never remember what to call the S combinator, but you can see what it does. When it receives on A, then it turns into a forwarder from B to C. And then the other one is the reflective combinator. So when that's in parallel with receiving P on A, then you just go back to being P. So that's the set of combinators and the rewrite rules, and we proved that this is equivalent to Rowlang. And so but the main trick is that now we have we've split the name producer into two kinds of name producers. There's a positive name producer and a negative name producer. And so this gives all of that. And then you can kind of, create this tower of typings. One is really dull. It's not very interesting. So you have an intermediate typing object. Looks like Mike is listening in. So you have an intermediate typing context, you have a typing context, which is either it's just lists of judgments that say a name is of type something and a process is of type something. Now, in the really, really dull one, a name is of type N, it's a name, and a process of type T, it's a process, and that's it, right? And then the type judgment rules are basically giving you how to construct well-formed processes and names, right? So that's these are the basic derivations. 0 is always well typed. If A is a name and P is a process, then you can make the message process. And so basically, this is just how to make well-formed terms. That's all this thing does. And then you can do a little bit better, which is that over in the typing information, you can know what kind of constructor you used, right? So, if A is a name and P is a process, then you form this, and that you lose information about which name you used and which process you used, but it's a message, right? If A is a name and B is a name and C is a name, and then you can form the duplicator on A, B, and C, but so it's a duplicator, but you don't know which names to use. That's the typing information, and so on. So this is kind of an intermediate step. And then we have, there's another piece that's kind of interesting, which is this cut rule. In particular, for each of these rewrite rules up here, for each of these, you're going to have some term formation that you're allowed to create. So I didn't show the par construction. And the par construction is much more constrained. You don't get to form pars willy-nilly. You only get to form pars that correspond to rewrite rules. So that's going to make sure that your system has some built-in safety around reduction. And then, around message passing, has some built-in safety around message passing. So if you've got some typing context over here, say delta, and delta thinks that D is well formed, and gamma thinks that M is well formed, then using gamma and delta together, so this comma, I should turn this into a comma. I think that's probably the simplest way to do it. There we go. Then delta, comma, gamma, so you mash them together as lists, thinks that when you put these in parallel composition, that whole thing is a term, right? Again, kind of boring, except that it's a little bit, it's not as boring as you might think, because you also have another rule, which is going to tell you that delta gamma also thinks that M, B, P, and MCP is of type T. And you get that as the logical sort of restatement of this rule here. So all of these rewrite rules will have kind of a left-hand side, which is the par formation part, and a right-hand side, which is effectively cut elimination. So it's the analog of cut elimination in this concurrency setting. So that's where this even boring system starts to get more interesting. And then it gets even more interesting down here, because now you can see the shape of the term. So delta thinks that D is a type D, N, 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 and gamma thinks that M is a type M, N, and T. Then delta together with gamma think that this par is like this tensor here, and then so this just says you've got a duplicator together with the message, right? So they have met each other. The duplicator and the message have met each other, and that's the left-hand side of that term rewrite. And then you can also get the right-hand side, which you derive from this, and this is again a kind of cut elimination. So you think of this as a cut. We cut these two terms together, and then we're going to eliminate the cut, passing over the rewrite rule, or passing through the rewrite rule, however you want to say it. And then this gets us the two messages. So this type transforms into this type. That's kind of the intermediate level. And now we're starting to see something interesting. A duplicator and a message becomes two messages. Type level information about information flow. That's neat. Now, the rich form of this starts to include the subtyping information. So we have a notion of kinds, which are a term is to a type as a type is to a kind. So these are sort of higher level things. These are not types, but you can think of them as schemas for types when you can write down type information. These should all be bolded. Go ahead and do that. And so you're going to get kinds for each of the term constructors, right? So you could think of this as like the structural types, right? They're giving you information about the structure of the thing that's in your hand. And then this is also a structural type, and this corresponds to the notion of par, and this corresponds to the notion of reflection. And then, and this one also should be bolded. And then, so this one here and these here are because we're saying that types don't just give you structural information, they say that you have sets of things. So this is the whole logic as a distributive law. So you've got some monad, which is your collection, you've got some monad, which is your term, and then the kinds are the combination of the term and the collection. So this is what Mike and I were working on last year, which is just getting the interaction of these monads worked out correctly, and being able to say, all right, the presentation of the monad is as a Lavoisier theory, but there's this correspondence between Lavoisier theories and monads, which allows us to sort of think about them as monads when we want to talk about the distributive law. We get to think about them as Levere theories when we want to see the details of the inner workings of the monad. So that's what's going on here. And there are basically two different flavors of kinds, right? There's the term flavor and the nominal flavor, which is, exactly as we would expect. That, follows the term construction up here. Terms, not names, that kind of thing. And then, so now where this comes into play is in this subtyping relation. And notice that we need this it's down here. So we need this when we want to do the more sophisticated cut rules. So here we're saying not only that delta thinks that DABC is of type D beta theta C, where these things are now these things are now types. So they're instances of the kinds that we were putting in before. So instead of in here, we have subsets of names that are described by the by beta, theta, and C. Similarly over here, we have gamma thinks that M is of type, bolded M. So structurally, it's a message, and the process is constrained to live in some set of processes psi, and the target of the message is constrained to live in the namespace alpha. So D is constrained to utilize or work only over the namespaces beta, theta, and C. And now, in order for these two to line up, remember, because you're duplicating this message, which means D is expecting A, something of A, but we've disconnected. So A could be in the alpha namespace here, and then the beta namespace over here. And so what we say is, well, the alpha namespace needs to be bounded above by the beta namespace, right? So it's more special, or it's more, you can think of this set as somehow contained in this set. So the menu of options for the duplicator is larger than the option, it contains the option that we picked, or the options that we picked. And under those conditions, then we can form this new term where they are in parallel, and we know that that's safe. We know that it's okay to be sending this message to this duplicator and having, and then we can take the final step, which is to go ahead and eliminate the duplicator and just get a pair of messages. Right, so that turns out to be sort of the motivating example for the subtyping relation, and I'll just quickly go through the subtypes. Types are so there's a top type, right, which corresponds to T, the term type, and top type is really a top. So if you have anything else, it's going to be a subtype of top. And there's a bottom type, and it's really a bottom. So if you have anything else, bottom is a subtype of that. And then the remainder of these things flows pretty much as you expect, right? Except that there's a covariance kind of thing going on. On the it looks like it ought to be the other way around. Did I get that right? No, this is correct. So if you know that alpha is a subtype of alpha prime, and you know that psi is a subtype of psi prime, then you can form message types, and they follow exactly as you expect. So the variance here is is the same because this is in positive variance, right? Remember, messages had a plus on the A part. So the subtyping is preserved by the message constructor, whereas for the duplicator, because the duplicator has the message in covariance form, notice that when we form the duplicator on both sides, it's reversed with respect to the subtyping relation, right? And this is kind of like what happens with subtypes and methods on objects and inheritance, right? The inputs to methods are like if you've worked in Scala, and you're trying to do some kind of parametric type on a method, then you've got to get the variance in the opposite direction. So that's what's going on here. And then but as long as you respect the variance covariance, then the type judgments, the refinements here follow more or less what you're expecting them to do for the term constructors. And so now that nails down the subtyping that we need to make these kinds of rules. So that's kind of at the in a nutshell what was worked out for over the last week. Hopefully that makes sense.
That's really cool. That's really cool. And there's a it's just types on types, ladle on ladle.
Well, I mean, it's basically everything that's necessary in order to write this kind of rule down, right? There's nothing here that isn't. So this is the guiding calculation for this piece of the puzzle, right? We need to have the proof rules work out so that when you form a parallel composition, that's forming a cut, and you can eliminate the cut by following the rewrite rule associated with the parallel composition. And once you understand that that's the guiding shape, everything else falls from that. And then the question is, did we get it right in ladle so that when we push this through, ladle doesn't break? And that's it turns out, lo and behold, it doesn't break. And even more nicely, the whole polarization thing lines up with the requirement of polarization for the trace story. So instead of generating more and more questions to be solved, it's all dovetailing. The pieces fit together, and we're getting more answers than questions. So that's the direction I like to see. When the moving parts keep generating more moving parts, then I get very nervous that's the sign that I've gotten something not right.
Or that the problem just isn't solved yet,
Yeah, exactly. But so this is
which is like not that normal. I'm
not when you're doing research, right?
I'm kind of really curious about this whole idea of like to what extent can and is it natural to like have different protocol layers, or to what or does it make more sense to just like have one protocol do like much of the work? So one question is like, okay, do you have a whole bunch of independent decisions? So like the nice thing about your virtual machine is that maybe I'm wrong. I don't know. So you have to somehow make this like decision on like the state of the virtual machine by like agreeing on the results of the race conditions.
Yeah, that's right.
Do you have the fact that like whenever there's a race condition, there's always only two alternatives?
Yes. Yeah, well, I mean, it can be reduced to a series of binary questions, but
are those, is it a series of binary questions that are independent of each other?
Yes, 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 that's right. So the place where that appears not to be the case is when you have, and actually we were working on this this past week. It's funny that you mentioned that. So at the high level row language, there's a select construct, right? So the select construct is actually really complex, right? It says each branch is a join, right? So if you just consider the simple case where you don't have a join, so you have, select from get y from x, select from get z from x, select from get, w from v, and select get, u from v, right? So that's a kind of select statement, and you have two different kinds of non-determinism, right? So you have the race, which is which of those wins, and remember there are four options as opposed to just two, and then you also have within each of the pairs you have a non-deterministic choice, like the y or the z or the u or the v. So, but that turns into a you code that down into a set of choices. So there's a whole synchronization protocol that's watching which of the options is winning and killing off the other branches.
Yeah. So this is what I'm asking. This is what I'm curious about.
Yeah. So
So this is kind of what happens when you try to do like a multiple layers approach.
Yeah.
I find. The other alternative is to have somehow instead of having to break things down into binary choices, do it out of to basically derive the consensus protocol around the logic that your system is evolving according to.
Yeah, I mean but here the binary, the way to think about it is or the way I think about it, maybe not the way to think about it. The way I think about it is very much in alignment with the way chemists think about it, right? So it is the case, and I'm fairly certain it's been observed, that you have ternary interactions and quaternary interactions. I don't think anyone's ever observed quinternary interactions. And as you go from binary to n-ary, the statistical likelihood of this happening, it just dramatically diminishes because in the natural world, it's just the conditions. It's hard for the synchronization to happen. Let's put it that way, right? That's why most chemists are very, very happy writing chemical equations down that involve binary interactions, right? That's why chemical equations are the shape that they are by and large, so the same thing is going to happen in Rolang, right? So people will be able to write down these large, sophisticated selects, but they're going to discover that in order to synthesize the machinery that makes that select chug along, it's going to, it's going to be costly. And the reason we were talking about this is because we're writing down the schedule of whatever the token is going to be. I'll just call it Rev, but it may not be called Rev. Rev to phlogiston. And so we have to calculate that for select statements. And there's a cost associated with the synchronization across the joins. And that cost is goes up the more you demand of the synchronization, right? Which is exactly the same as in thermodynamics, right? It's like, it's a much greater cost to try to synchronize 3 particles or 4 particles or 5 particles, right? And so then the trade-off becomes, well, do I write my own set of binary interactions that's going to get me the overall behavior that I want of this inner interaction? In other words, do I code up that myself, or do I let the system synthesize it? And if I don't need all of the options, if it's unfair in one way or another, then it's better to code it up myself. Because the system's going to code up something that's sort of maximally fair. And that's why the user is paying.
You mean it's not better for you to code it up?
So if it turns out that there's some asymmetry in their program or their contracts, so that not all of the options that are associated with a fair select or a fair choice are present in their actual protocol, then it's much better for them to code it up, as a set of binary interactions, right? Because they'll pay less cost, and their code, may not be much more sophisticated. And you can
how do you know the cost of like a more expensive synchronization?
Well, because we'll give you the price schedule. We're telling you exactly.
Yeah.
We're telling you exactly how we build the state machine and what it's going to cost you to build that state machine on your behalf.
I understand about state transitions, but I think it's a little bit different if you're thinking about consensus messages, because you don't want. So when I have a transaction, I don't want to be screwed just because they took extra messages to come to consensus.
Well, this isn't even consensus, right? This is just. It's a limited form of consensus. All it's saying is, a select statement is kind of like a limited form of consensus with a limited fork choice rule, right? The forks are all listed out. It's each of the different branches of the select. So this is at the language level rather than at the consensus, the Casper level that we've been talking about, right? I'm just drawing an analogy here, right? So the select is like a little mini consensus, right? But you only get, however many forks as our branches in the state.
So how do you decide on how much, say, like, a combinator with like 3 or 4 or 5 would cost?
So again, the way it's done is per name. Per name space, you have costs that are associated with read and write. So if the namespace is associated with directly writing memory, in other words, these are variables, and they're never going to go to store, you still want the contract to pay a cost, but they don't have to pay a cost of hitting storage or reading storage, right? So it's a different kind of cost. So effectively, the cost function gets carved up over the different kinds of namespaces. So there's in-memory namespaces. There's to-store namespaces. So those are observable values as opposed to the as opposed to ephemeral values. And then there's comms, right? So if it only ever goes to storage but it doesn't ever hit the network, then you don't pay the network costs. If it only ever goes to network but never hits storage, then you don't pay the storage costs, right? So there's and there's if there's write contention, then there's going to be overhead on the consensus. Yes, that's correct, but that's at the consensus level as opposed to the. This is you're going to pay. How do I see this? You're paying for Casper Casper, think about it this way: if we get it right, then Casper is a bunch of contracts above this basic mechanism, right? So you have we'll write most of the contracts in Casper in Rolang itself, and then when we're self-hosting, we can rewrite the whole thing in Rolang. So you can calculate from basic storage and memory and comms a layer above that, which is the consensus mechanism, and that's going to give you whatever the additional cost is.
Yeah, so that's kind of what I'm saying. I want to pay extra because people are like crappy at coming consensus. They could like use it as a way to like scam me out of gas by like using more messages than necessary.
Yeah, agreed. One interesting point that's come up is also we want to be able to give detailed information about space versus time trade-off. So I'm thinking about making phlogiston be something akin to a complex number. So it's got two components, but you can, just like with complex numbers, you can still multiply them, add them, subtract them, yada yada yada.
Does it have like a market price in storage and a market price in bandwidth? But like those aren't independent market prices. You have to trade them both at the same time.
Yeah, so I haven't had the balls to push it up to that level. I've long had the intuition that something like that should happen, that you have to pay in two different currencies at the same time.
No, it's definitely true. But the kind of like, another kind of truth is that like people like basically like standardization increases liquidity.
Yeah, exactly.
Increases usability.
Yeah, exactly.
So like if you want to have like the most standard thing you could possibly think of, especially for a small market. If you have a huge market, then it can probably support all sorts of crazy.
Oh, it's better because I mean the markets basically live off of shell games, right? You got this giant feature space.
No,
right?
I mean, I think it's also bad from the point of view of like transaction costs of people using the system if they have to cross more spreads.
Yeah, I mean, I understand, but like I recognize this when I went to buy my RAV4, whatever it was, almost 20 years ago. Like the guy was trying to say was basically trying to buffalo me with feature space, right? He was like, well, you've got the leather seats with the the anti-lock brakes versus the finish on the car. I can't even remember all the features, right? And the trick was to track the value as it was shifting. Is it under this set of features or under this set of features, and for different folks, it's going to be, the value is different. It's not the same coin. It's not the same ball under the same cup. So to speak.
I hear you. No, I think it makes a lot of sense. I really do. But I also think it makes sense to just like kind of have gas and call it a day. Because basically like you're asking for an order of magnitude more complexity than the current Ethereum gas system due to the fact that like people now need to know, okay.
Well, again, the thought was that by the time you get to a staking currency, it's a number. And then the phlogiston itself, the phlogiston is a number too. It just happens to be, a complex number, not a real one.
Yeah, but is it a constant complex number, or does it change over time based on market conditions?
No. Well, I mean, ultimately, you'd like to be able to, if it turns out that market conditions mean that space is cheaper than compute, then you'd like to be able to have a phlogiston schedule that reflects that.
No, I completely agree. No, I think that's correct. But I'm just saying, because it's weaker standard, it leads to less liquid markets, which means and also more markets, which is like slightly more difficult to deal with. One thing you can do though is like, hey, now that we're over here anyways, we can provide a market for like derivatives in order that you can like lock down the needs of your application. Futures, like futures for gas. Like, I think futures for gas are just like waiting to happen.
Absolutely. No, totally.
I've had a design for it for like maybe a year. Basically, just like you have the consensus protocol allocate future gas, and like it enforces the settlement and delivery of that gas. Because like if that block doesn't include that transition, then like it's invalid.
Yeah, no, I think absolutely. But it also applies to the other side, which is the futures on the actual resources, right? Because I mean, it's not going to be the case that just every agent on the network is ponying up resources. You should talk to Nash Foster, because he's got some.
But that's a little bit. It's a different kind of market. You have like independent buyers and sellers. Whereas like
they fit,
consensus,
right?
whereas for consensus state transitions, you can kind of like treat the sellers as like this one big like group of miners who's selling you like one service as like one collective.
I hear you. I hear you. I'm noticing that it's 8:11, and so this is a really good conversation. I've got a 9 o'clock that I have to prepare for.
Okay. Anyone else have any last words?
That was awesome.
All right. Great. Good last words, Carl.
Yeah. All right, guys. See you next week. Ciao.